Senior Plasma Physics, Lecture 2. Before we get on to the collective effects of a plasma, it's quite informative to treat the motions of the individual particles that are subjected to electric and magnetic fields. That is, we assume that the particles don't interact with each other. We do this for several reasons. That is, we introduce the equation of motion, called the Lorentz equation, and this equation appears in all sorts of theoretical treatments of plasmas, not just of individual particle motions. In all of this, we will assume that there are no relativistic effects. They can easily be included. We do this for simplicity, and it covers most of the plasmas that we will meet. We're also assuming that the particles are collisionless. We will certainly treat collisional particles later. Because we're assuming that the particles are collisionless, that means we're also assuming that they are of very low density. As we'll see, there are low density properties of plasmas that do translate into plasmas of higher density. In treating the plasma as consisting of single particle motion, we introduce the idea of cyclotron motion and its associated cyclotron frequency. This parameter appears throughout all sorts of treatments of plasmas in magnetic fields. Finally, we'll look at a magnetic effect known as diamagnetism that arises in plasmas but also arises in other materials, which we'll talk about briefly. The force on an individual charged particle is given by the Lorentz equation and is this expression, where the symbols have the usual meaning: force, mass, the charge on the particle, the electric field vector, the velocity vector, and the applied magnetic field vector. So now let's apply the Lorentz equation to a particular situation, where the electric field is zero and the magnetic field is uniform in space. So here is the Lorentz equation, but now missing its electric field vector on the right-hand side. You'll find the problem becomes much simpler if we make a convenient choice of the magnetic field direction. Remember that the magnetic field, in this case, is uniform. So we can rotate our axes such that the magnetic field is along the z direction. So we can rewrite the magnetic field vector as a much simplified vector of B along a unit vector k, which is along the z direction. Now all that remains to do is to obtain the cross product of V cross B and substitute it into the Lorentz equation. Because we've chosen our magnetic field vector to be along a very convenient direction, so we choose a general direction for the velocity vector, given by this expression. So the velocity vector has components Vx, Vy, and Vz, indicated by the unit vectors I, j, and k. And just remember that our magnetic field vector is along the z direction. Now we need to obtain the cross product V cross B. Now there are a few ways to do this, so feel free to do it any way you like, but here is the way I do it. The cross product can be obtained from a determinant of the two vectors, where the top row is the row of unit vectors I, j, and k. The middle row are the components of the velocity vector, and the last row are the components of the magnetic field vector. If we carry out this determinant, we end up with the following expression, which consists of x, y, and z components of V cross B. Notice that the z component is 0, indicating that there is no force on the charged particle in the direction of the magnetic field, as you might expect. All that needs to be done is now we substitute this expression into the Lorentz equation, given by this. So the left-hand side of this equation can be expanded into its x, y, and z components. We equate that to the right-hand side, which we've just obtained from our cross product, except now we've added the charge q. We now need to equate the x, y, and z components of the left-hand side to their corresponding components on the right-hand side. So for example, the x component on the left-hand side can be equated to its corresponding x component on the right-hand side. In the same way, we can equate the y component on the left-hand side with the y component on the right-hand side. And the same thing can be done for the z component. Now let's rearrange the top equation so that we make Vy the subject, and we substitute this into V of y of the y component. That means we now end up with a second order differential equation in V of x. So let's rearrange this resulting expression into the following, where the second order derivative is now on the left-hand side by itself. So we can carry out the same procedure for the y component. So as a summary, we end up with two second order differential equations. The first one you've seen, which we've just derived for the Vx component. And in the same way, we can have a second order differential equation for the y component. Now, both of these equations can be written in a slightly more compact form, where we've replaced the QB on M of the right-hand side with omega c. And the reason we've done that is because this form of second-order differential equation is the classic simple harmonic oscillator equation, where Vx and Vy are sinusoidal functions, and they are 90 degrees out of phase. If Vx and Vy are 90 degrees out of phase, and they have the same amplitude, then that combined motion is circular motion. We refer to this for charged particles as cyclotron motion. So let's expand omega c in terms of this, where omega c is referred to as the angular cyclotron frequency, and Fc is the cyclotron frequency. Please don't confuse the angular frequency with the cyclotron frequency, although frequently in books omega c can be referred to as cyclotron frequency. We will not be doing that in this course. So now let's look at some terminology associated with cyclotron motion. So imagine we have a magnetic field that's into the page in this case, and we introduce charges, both positive and negative, into the field at a certain velocity. And from your undergraduate years and even high school years, you can use a hand rule of some kind to work out the direction of motion of these particles. Strictly speaking, we can actually solve the equations of motions that we've just derived to show the resulting circular motion. However, in this case, it's just as informative to use some kind of hand rule to indicate their direction. So the radius of this motion is called the Larmor radius and can be quantified by this equation. You'll recognize the form of this equation from classical circular motion, where RL is the Larmor radius and V perpendicular, or V perp for short, is the velocity component, or if you like, the speed at right angles to the magnetic field. Notice that V perpendicular can be Vx or Vy or combinations of them, but in the end they can both be combined to form a constant speed V perp. And we substitute the expression we've just obtained for omega c on the right hand side. Finally, we'll look at a phenomenon known as diamagnetism, which not only occurs in plasmas but other states of matter. Again, imagine if you had a magnetic field, in this case out of the page, and we inject charged particles into that field. Again, use whatever rule that you're familiar with to work out the direction of motion of the charged particles. Hopefully you would have found that the positive charge on the left-hand side moves clockwise and the negative charge on the right-hand side moves anti-clockwise. Now, the circulating charges constitute an electrical current. Again, use another rule to work out the magnetic field generated by a circulating current. Hopefully you would have found that the magnetic field generated by the positive charge is into the page, and the magnetic field generated by the negative charge is, again, into the page. That is, both charges have generated a magnetic field of their own because of their circular motion that opposes the direction of the applied magnetic field. You can imagine that this will produce a repulsive force between the circulating charges and the applied magnetic field. This phenomenon of producing an opposing magnetic field is known as diamagnetism. You would have seen this phenomenon before. Probably the most well-known phenomenon is diamagnetism in superconductors. This has been referred to as the Meissner effect, but really the phenomenon is known as diamagnetism. You also get diamagnetism in water, but the difference between the diamagnetism in water and superconductors is that superconductors produce perfect diamagnetism. The opposing field they produce is equal in magnitude to the applied field, but water produces a much weaker opposing field. And there are many more examples.